So now that we know how pH influences solubility, we're going to take a look at the process of solubility equilibrium from the other side, which is looking at when we're mixing two solutions that contain ions that could form a precipitate. The question is, will a precipitate actually form, or will it not? In Chem 11 or Gen Chem 1, when we discuss these type of reactions, which we call double displacement reactions, we always assume that if an insoluble salt is formed, then automatically a precipitate will actually show up. But that's not always the case. And so in this section, we're going to discuss the concept of predicting whether precipitation will occur or not. And we're going to have to start by just looking at how that process happens. So if you have a solid and it's dissociating into ions, so that's sort of the process that we're considering here. There's two reactions that are happening: the dissolution of the solid into ions and then the reformation of the precipitate by the ion, right? So we get that forward and reverse reaction going. So we're going to have to think about which reaction is dominant. Is it the forward reaction or is it the reverse reaction? So when we initially put a precipitate in a solution, all we have is just no ion floating around. So this is the picture on the left. It's just a bunch of the precipitate that's originally there. The solution there is still just pure water. So at that point, what's going to happen is only forward reaction, which is solid dissociating. Some quantity of that solid is going to dissociate. And so that's represented by the pink arrow there. Once some ions are floating around, so you can see the color of the solution has changed now, then the reverse reaction, illustrated by these black arrows, where the ion reform the solid, is going also to happen. Now, again, the rate at that point might still be higher in the direction of the dissolution of the solid, but at least both processes are happening. And of course, eventually equilibrium happens where both rates are equal to each other. So that's illustrated by the two arrows having the same length. And at that point, you're not going to get any more formation of precipitate or formation of ions. They're just going equal to each other in terms of rate. And so when we reach equilibrium, where we have the maximum amount of ions we can have in that solution, that's what we refer to as a saturated solution. It just means that we can't put any more ions in there. It's maxed out. That's the most we can do for that particular ionic compound. Now, the limit of the ion that's placed in there is what we refer to as the solubility. So we have discussed this before. And of course, different salts have different solubility. This plot right here just shows you a few different salts and their solubility. So you can see NaCl there given in the black line, showing you how the solubility increases with temperature slightly. There's some other salt like potassium nitrate that increases a lot more dramatically with temperature. But at different temperature, the amount of ions that are going present at equilibrium with the solid is going to be different. And that makes sense because this is an equilibrium, so it's going to be affected by temperature because we know the equilibrium constant is affected by temperature. And so we call these type of curves solubility curves. Again, it helps us know what the different solubility limits are for different salts at different temperature. So we just talk about that idea of a saturated solution when you've maxed out the amount of ions you can have in the solution at equilibrium with the precipitate. Now you can also go below the saturation limit, so you just don't put as much ions in there, right? And that is possible. At that point, of course, you're not going to see any precipitate because the concentration of ions combined together is not enough to actually generate a precipitate. So when we have that, that's what we refer to as an unsaturated solution. So it's just below saturation. We haven't reached that limit yet. So at that point, the rate of the formation of the precipitate is a lot less than the rate of the solution. So if you look at your beaker at that point, there's no precipitate in an unsaturated solution, just because at that point, the black arrow is much, much smaller compared to the pink arrow here. So all the solid that forms completely breaks apart immediately, whereas the formation of the solid is so slow that it doesn't keep up with the dissolution of the solid back into ion. Now, we also have a situation where it's possible that when a solution is saturated, we can heat up, bring up the temperature higher, and then increase its solubility. That's what's shown by all of these solubility plots, right? So if I have KNO3 at about 10 degrees, the solubility is right right here, about 22 grams, let's say, in 100 grams of water. But if I crank up that temperature to 40 degrees, all of a sudden the solubility is now 60 grams. So a lot more KNO3 can dissolve in that same quantity of water. What's interesting is if you slowly cool this back down to 10 degrees, sometimes all of those KNO3 that was dissolved will stay dissolved even at the lower temperature. So this solution here is what we refer to as a super saturated solution. You're not supposed to have that much KNO3 at the lower temperature, but you're able to trick the system to make it happen. However, this is a really unstable system. You have way too much concentration of ion at that temperature. So one of the things that we use this for is to create crystals of the compound, because if we put a small amount of crystal into the solution right now, you will see instantaneously that the solution will turn into this form right here. And so these are needles of crystals that are formed by the compound, let's say KNO3 in this case, because it was just at such high concentration and at that low temperature that can't last. So that's just a discussion about saturation and unsaturation and supersaturation. Now we're going to take a look at how the rate of dissolution and the rate of precipitation can be used to predict whether a precipitate will form or not. The reaction looks something like this. You have a solid going to the ion form. The solid, of course, is the precipitate. The ion form is the clear solution. If the forward rate, so going this way is dissolution, is going to be less than the reverse rate, which is the rate of precipitation, then at that point you expect precipitate to occur. And so the precipitate is formed at a higher rate than they're able to dissolve. So that's condition 3 right here, okay? So it's showing you that the rate of the ions going towards the precipitate, the reverse rate, is greater than the forward rate. Vice versa, if you have the dissolution rate, but if that rate is greater than the rate going backward, then now, as soon as the precipitate forms, it's going to dissolve. So you're never going to see a precipitate. And so that's condition A right here. No precipitate has ever formed. Okay. And so what happens when both rates are equal to each other? Well, you'll see a small amount of precipitate, and that's what we refer to as the equilibrium condition, right? So when they're both just equal to each other. Again, you have these 3 situations where you'll see no precipitate, you see a lot of precipitate, or you see a little amount of precipitate when the 2 rates are just equal to each other. Instead of using rates, we can also use equilibrium constants, since we're analyzing a point where the reaction reaches equilibrium, which is when no more precipitate can dissolve in the solution. So instead of comparing 2 rates back and forth like what I just did, you can remind yourself that rate of forward and reverse reaction could be connected to the equilibrium constant by using a relationship we learned a while ago in kinetics when we talk about elementary reaction. So we can rearrange this expression of the 2 rate, which is shown right here, and just express it so that you have just the ratio of concentrations on one side and then the ratio of the rate constants on the other side. Once we have the ratio of the rate constant, that's just equal to the K value, and then the ratio of the concentration is just the Q value. So now instead of comparing 2 rates, we're just comparing the values of Q to the values of K, and using the same thought process, we can summarize the relationship as follows. So if the Q value is greater than the K value, then precipitation should occur. And again, this should be analyzed using the reaction where you have solid on the left side and your ion on the product side, right? So the Q here is just the concentration of the A plus times the B minus in this case. And if that number is bigger than the K, then the reaction would shift to the left as we expect. And shifting left, that you're going to form precipitate. Okay, so that's why precipitation will occur in this case. If Q is less than K, as we know from our equilibrium discussion, then the reaction would shift to the right, and that forming the ions here, no precipitate, so then don't see any precipitation. And then lastly, a solution would just hit equilibrium when the Q is equal to K. And again, using this, we can now predict if I have a certain concentration of ion in my solution, whether I will see a precipitate or not. And this is illustrated really using a plot like this. So you can draw a curve right here, right? Every point on that curve is where Q is equal to K. At different ion concentrations, this is referring to the AgCl precipitate, So if I have a lot of silver ion, then the concentration of the chloride ion that is needed to start generating precipitate will be pretty small, right? Because the Q expression is just Ag plus times Cl minus. Okay, so if this number is really large, that number for chloride has to be really small because the product has to equal KSP, start seeing a precipitate. So this is a constant. So if one number goes up, the other number has to go down. And similarly here, when the chloride ion increased by a lot on the right side of this x-axis, then the value of the silver ion concentration has to be small. So again, this whole curve here just tells you where different equilibrium points lie with different concentrations of silver and chloride ion. Now, if you're on this side of the curve, right, on this part of the curve, then you're basically having a lot of precipitate because at that point your Q is much larger than K. However, if you're on this side of the curve, then you are below saturation. So at that point, you don't see any precipitate. Okay, we'll actually do an example here just to kind of show how these calculations are done. So the first example here just says if we have 3 drops of 0.2 molar Ki and we add that to 100 milliliters of PbNO3, will you see a precipitate of lead iodide form or not? Okay, so you're told to assume that 1 drop is about 0.05 mil. And so let's do that calculation. The first thing we need to do is just kind of think about what the reaction looks like, right? So the possible precipitate that could be formed there is PbI2. So it's PbI2 solid goes to Pb2 plus and 2I minus. One of the things that students always sort of get a little confused about is that we don't have a precipitate that dissociate, but we're trying to mix the 2 ions together, this and this ion, to see if we're going to form precipitate or not. So why is the reaction written as if we have a solid going into ion? And the idea that I want to get across is like, it doesn't really matter how you write the reaction, right? Because this is a reversible reaction, so it could go both ways. It's just that the KSP is defined with respect to the solid dissociating into ion. So we have, since we're comparing to KSP, we have to write the reaction this way. Okay, but the idea is we're analyzing, in this case, the reverse reaction, which is when the 2 ions are combined together, will we see a precipitate or not? And to do that, we're going to have to compare Q to K, just like we discussed in that notes earlier. So QSP versus KSP and see which number is larger or are they equal to each other. In order to do that, I'm going to have to use the K expression. For this particular salt, the K expression is going to be just Pb 2 plus times I minus squared. So I'm going to need concentration for both of these ions. I can calculate it using my standard dilution calculation here, M1V1 equals M2V2, because I'm mixing 2 different ions, right? So for the iodide, I started with a concentration of 0.2 molar. It's 3 drops, each drop 0.05, so 3 drops, 0.15 milliliter. And then this bottom number here is the total volume after you mix the iodide and the lead ions together, giving you this new concentration for the iodide. This is before reaction happened. And then the lead, we can similarly calculate it. The lead is much larger volume here, but same total volume. And then this is the concentration of lead at the beginning before reaction happened. And then we can then calculate our QSP, which is just this expression. That gives us this number right here, 8.96 times 10 to the minus 10. Now the KSP value wasn't given in the question, but you can search it up either in your textbook or online, and you'll find that the KSP for PbI2 is in the order of 10 to the minus 8. So one number I found is 1.4 times 10 to the minus 8. And given that the number we just calculated is a smaller number than the KSP value, so Q is less than K, so we don't expect to see any precipitate here. So if I were to visualize this, I have my lead ion solution in here. I added 3 drops of I minus into here, and what I expect to see is nothing in terms of a precipitate. It's still a clear solution.